Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our discussion of AP Physics 1 Unit 5 now, which is on torque and rotational dynamics, and we're going to go over our big three kinematic equations for rotational dynamics. Okay, so the good news is, as we dive into this, all of the equations that I'm going to be writing today are extremely familiar to you. You guys know these three equations in green here on the board really well, right? These are just our big three kinematic equations for linear movement and all of that. The big three equations that you guys are used to. The good news is the three equations that we're going to be using a lot for rotational motion are exactly the same, just with a couple letters swapped out and slightly different units. And when I mean exactly the same, I really mean it. So here, our first equation, our final velocity is equal to our initial velocity plus acceleration times time. All that becomes is that my final angular velocity, which I represent with this little squiggly w, this squiggly w is actually a Greek letter called omega. It is a lowercase omega. And one thing that you'll notice as we go through all of these equations for angular motion is that they have a lot of Greek letters. And that's just because we ran out of normal ones and we had to borrow some from another alphabet. But no different from an X or Y or Z, it's just a lowercase omega, squiggly w. So our final angular velocity is equal to our initial angular velocity plus our angular acceleration, which I represent with a squiggly a or a lowercase alpha, times time. And time is the same as it used to be. Okay, that's not too bad, just a couple letter swaps, but it's otherwise exactly the same kind of relationship. Here, our second equation, that our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our displacement. Well, all that becomes is that our final angular velocity squared is equal to our initial angular velocity squared plus 2 times our angular acceleration times our angular displacement. And instead of x, I use a theta to represent angular displacement. Okay, and then this third one, our displacement is equal to our velocity times time plus 1/2 acceleration times time squared. All that becomes is that our angular displacement, or delta theta, is equal to our angular velocity times time plus 1/2 our angular acceleration, times time squared. And so all of our angular rotational motion equation things, that's the technical term, are direct analogs to all of the equations you guys are already masters at using. So, and in fact, the way that we use them is going to be very familiar to you as well. It's just making that transition from linear movement to rotational movement is kind of tricky at first, but once you wrap your brain around it, the math is very similar. Thankfully. So I'm going to erase these here so I have room. And let's go through an example problem. So this is our problem here in blue. We have a ceiling fan that has an angular velocity of 0.3 revolutions per second and a diameter of 77 centimeters. It speeds up with an angular acceleration of 0.9 revolutions per second squared over 0.5 seconds. And we're asked to find its final angular velocity and its angular displacement. All right, so first, let's make a list of everything that we know. Well, we know that we have an angular velocity of 0.3 revolutions per second. So I'm going to make a little cross of my nose. I've got my angular velocity of 0.30. Oh, and this is my initial angular velocity of 0.30 revolutions per second. I have a diameter of 77 centimeters, which means if I'm going, well, we'll skip for that for now and just underline it. We know that it speeds up with an angular acceleration of 0.9 revolutions per second. So that means we know our angular acceleration is 0.9 revolutions per second squared. We know that happens over a period of 0.5 seconds. So we know that our time is 0.50 seconds. And we know that we're trying to find our final angular velocity and our delta theta. So now you might be tempted to just start plugging these values into our equations and go off to the races. But wait, before you do, we need to notice the units that we're using here. If you watched our video on unit conversions, then you will know that anytime we plug our values into any of our equations here, we need to make sure that we're using the proper SI or standard international units to do so. Just like we have to make sure our mass is always in kilograms, we have to make sure all of our angular units are in radians. And right now they're all in revolutions. So we're going to have to do a couple of quick unit conversions before we can get started. So let's first start with our value for our angular velocity. It's 0.3 revolutions per second. We know that that is equal to 0.3 revolutions per second, and we're going to convert it using our little train tracks. Well, if we're trying to convert to radians per second, how many radians are in a revolution? 2 pi. So we know that there are 2 pi radians per 1 revolution. My revolutions cancel out. I'm left with radians per second, and this is equal to 1.885 radians per second. And that is with the proper units, so we're good to go now. Also, our acceleration, our angular acceleration is in 0.9 revolutions per second squared. I need that to have units of radians per second squared. So 0.9 revolutions per second squared. I'm going to do my little train tracks. It's going to be the same conversion, so times 2 pi divided by 1. There are 2 pi radians per 1 revolution. My revolutions cancel, and I am left with 5.655 radians per second squared. Okay, I'm going to have to erase these 3 equations, but just remember they're exactly the same as our original 3 kinematics, just with our English letters swapped for Greek ones. Okay, so now we have our value for angular acceleration, we have our time. I'm also going to note that we have a diameter of 77 centimeters. That might come in handy later. I don't know. We'll have to see. Okay, and is that all of my values? And we're trying to find our final angular velocity and our angular displacement. Okay, and now I'm going to erase this so I have room to work. Okay, so if we think back to our big 3 equations, well, first I need to find my final velocity. Well, just like in our normal kinematic equations that we're used to, I can find my final velocity if I have my initial velocity plus my angular acceleration times time. Well, all of these are values that I have, so I'm just going to go in straight ahead and plug in and let's go. So my initial velocity is 0.30. Oh, oops, sorry. 1.885 radians per second. We need to make sure we use the ones with the correct units. Don't make that mistake. So this is 1.885 radians per second plus my angular acceleration, which is 5.655. I'm going to round a little bit, 5.66 radians per second squared, times my time, which is 0.5 seconds. So now if I plug all of that into my calculator and solve, I end up finding that my final velocity is 4.71 radians per second. And we can double check our units. Our first term here has units of radians per second, so that checks out. Our second term here has radians per second squared times seconds, so my seconds squared cancels out my seconds, and I'm left with units of radians per second here. Radians per second plus radians per second gives me radians per second. That all checks out. Those are the units I want, and so now I know that my final angular velocity is equal to 4.71 radians per second. Okay, that wasn't so bad, right? That was just like what we did back in Unit 1 with kinematics, just with squigglier letters. Okay, now we know that the second thing we're trying to solve for is delta theta. And good news is, because we've solved for our final velocity, we could either use our equation number 2 or 3. Both work, neither are wrong. You just get to pick whichever one you like more. And I personally like the second one more, because, or option number 3 more, because I don't like having to square root stuff. But both are correct. So if you get to this point and you are like, oh no, both of these equations work, there can only be one right answer, there can only be one way to get to what I'm trying to solve for, what should I do? Don't fret, there are actually more than one right way. There is actually more than one right way to get to the answer here. We're just pick whichever one you like more, roll a die, flip a coin, any way works. But in this example, we're going to use equation number 3, which is that our angular displacement is equal to our initial angular velocity times time plus 1/2 angular acceleration times time squared. So now I have all of my values and I can just plug directly into these. So this is our angular velocity is 1.885 or 885 radians per second plus 1/2. My angular acceleration is 5.66 radians per second squared, pardon my terrible handwriting, times, oh, I forgot my factor of time here. Let's back up and put that back in there. So our initial angular velocity times time, so times 0.5 seconds, plus 1/2 my angular acceleration, which is 5.65 radians per second squared, times, I'm running out of room, okay, times time, which is 0.5 seconds squared. That really is bad handwriting. Okay, but once we plug all of that into our calculator, just like we know how to do very well, we end up finding that our delta theta is equal to, this first term becomes 0.9425, this second term here becomes 0.7069, and then I add those together and we end up getting that our delta theta is equal to 1.65. But I'm not done, that's 1.65, but 1.65 what? Well, all of our values have units of radians per second times second, seconds cancel out. This is 1.65 radians. So keep that in mind, keep track of your units. That is one of the easiest ways you can either miss a question or figure out that you missed a question, is double checking your units at the end. And if you ever don't know what to do, looking at your units can often give you a nice little roadmap of the path you need to take to victory. So here our delta theta is 1.65, our final angular velocity is 4.71. We ended up finding everything that our question asked us to do, so now we are done. We can take a deep breath, relax, go swim, but not if it's December. But yeah, one little note, we were given our diameter in this problem, but we didn't end up needing to use it. That you'll see a lot on the AP exam. Just because a question gives you information doesn't mean you need to use every single piece of information that was there. So don't be tripped up if that happens to you. Maybe double check, make sure there wasn't anything that you needed to use a diameter or a radius to calculate. Once you've double checked that, you can take a deep breath, put down your pencil and go take a break, watch a movie, eat a snack, do something. Anyway, thank you so much for sticking with me through all of that. Y'all are troopers and happy physics day.